Now we want to talk about Krull intersection theorem. So let A be a Noetherian ring with an ideal this A, and this ideal A is contained in all the maximal ideals of A. So then you take the intersection of this A raised to the n greater or equal to 1. This is just 0. So to prove this, we are going to use Nakayama's lemma. So in fact we are going to show that this we can decompose as a product A times again intersection of this n greater or equal to 1. So if you have this, then by Nakayama lemma this is just 0. So this is what we have to show. So before we can start, we have to first describe what is this ideal A raised to the n. So let this ideal A, this is our ideal, which is the primary motive of study here, because this ideal A is contained in all the maximal ideals. So this is the ideal which is important for our theorem. So this ideal is in a Noetherian ring, so it is generated by a finite number of elements of the ring, A1 to say AP. So then we can think of this A to the n as some homogeneous polynomial f. So this is f is a homogeneous polynomial of degree n, and this f we are evaluating at this point A1 to AP. And where does this f come from? This f comes precisely from this ring of polynomials. You have A x1 to xp. So this is important to understand what A to the n looks like. And so if you want to write it more formally, you can say it's a sum C j1 to jp. This is just the constant which comes from the ring, and you have this elements a1 to the power of j1 times a to the power of j2 all the way to ap to the power of jp, and you add all these j's up. So that is j1 plus j2 all the way to jp. You add them up, you just get n. So this is more concrete description, but for this problem we have to think in terms of homogeneous polynomials of degree n. So we already know if ring A is Noetherian, by Hilbert-Basis theorem, if you attach this x1 to xp to A, this polynomial ring will also be Noetherian. So our strategy is this. We already know A to the n. When we talk about it, we talk about homogeneous polynomials. So if you are talking about some element A prime which is contained in the intersection of A to the n, then A prime has to be a polynomial of very high degree. And this high degree polynomial will be generated from some set this. So we will talk about this set in a bit. So the idea is we are going to be working in a Noetherian ring. So even if we have a polynomial of very high degree, so this A prime would be associated to some polynomial h of very high degree. This polynomial h we can write it as f1 g1 plus f2 g2 all the way to fs gs, where this g1 g2 all the way to gs are generators of this set, and this f1 f2 everything comes from this ring here. So we are able to finitely generate h, so that is critical. So once we are able to finitely generate s, then we will argue that this A prime is just h evaluated at a1 to ap. That is just the definition of A prime. This we can write it as fi times a1 to ap times gi a1 to ap. So this gi's, this g1 to gs, we will show that this is what is going to generate this intersection. So this product will become, this gi's will generate the intersection, and we will show that these fi's are not constant, so they lie in the ideal A. So this A prime would lie in A times intersection of an, where n is greater or equal to 1, and we notice that this A prime has been chosen from here. So we have this decomposition like this. So now we have to fill in the details. So let this S sub m be the set of homogeneous polynomials of degree m, which lie in this intersection of all these ideals. So they are just degree m. So now we start taking polynomials of degree 1, degree 2, degree 3, and so on. So then we can construct an ideal B, which is generated by a union of all these polynomials of degree m which lie in the intersection. So union of all the polynomials of degree m which lie in the intersection is essentially generated by homogeneous polynomials. So we have this Noetherian ring A x1 to xp. B is an ideal of this ring, and B is therefore generated by some finite set of generators g1 to gs. So say G1 has degree D1, G2 has degree D2, all the way to GS has degree DS. So let D be the maximum degree of all polynomial GI. So degree of polynomial GI is DI as generators of B. So what have we done till now? We just said that all the polynomials which lie in the intersection, they essentially get generated by this ideal, because we have just taken the union of all degree m polynomials here. Now if you pick up element a prime in intersection of n greater or equal to 1 an, and we are saying a prime is polynomial of some high degree, then its minimal degree has to be at least d plus 1, because the single element d is not going to be able to generate it. So its minimal degree has to be greater or equal to d plus 1. So this high degree has to be at least d plus 1. And now we have this set of generators, so we can write this h as of the form f1 g1 all the way to fsgs. So this polynomial h, this is of higher degree. It has to be generated from this union, because this union contains the union of all degree m polynomials which will lie in the intersection. So you can write it like this. So degree of h, so all these terms are homogeneous of same degree. So this is homogeneous polynomials. So degree of h has to be equal to degree of this term. Degree of this term is degree of f1 plus degree of g1, but degree of g1 is d1. So all these degrees have to be equal. So this will be degree of fs plus ds, where ds is degree of gs. So if you take the minimal degree here, if this is d plus 1, and the maximal value of d1 can be d, so we have that the degree of f1 or degree of fi has to be at least 1. So again, degree of h is greater or equal to d plus 1. So the none of fi are constant, because they have to have degree at least 1. So therefore you can show that this fi lies in a, because it's not a constant. This gis will lie in intersection of a and, because these are the ones which are precisely generating the intersection, as you can see. So they generate this entire union, but this union consists of all polynomials of degree m which lie in the intersection. And that is the end of the story. So you see that everything hinges crucially on this fact here, that if you choose polynomial h of high enough degree, it has to have minimum degree of at least d plus 1. And this comes from the fact that maximum degree here is d. So if you take polynomial which lies in all the intersections, it has to have a slightly higher degree, because a single element here would not be able to generate it. You have a set of generators. So recall what radical of I is. Radical of I is all the elements a in the ring A such that there exists some natural number n, such that a to the n lies in this ideal I. So you just pick up all elements in the ring, so that some power of them will lie in the ideal I. So our example is radical of 0a, which is called the nil radical. It consists of nilpotents. So all the elements, if you raise to the power, some natural number, they will become 0. So obviously radical of I would contain our ideal I, because if you put n as 1, this containment will be there. You can see more precisely these nil radicals. They obviously, nil radicals, radical of 0 will contain 0, but it also contains other nilpotent elements whose power will become 0. Now the idea what we want to expound in this lecture is that if we work within a Noetherian ring, then something miraculous happens. We can raise all the elements to a single big power, and they will come back in I. So for example, say you take a nilpotent element a. So a to the n is 0. Then say there is another element b, which is say b to the n2 is 0. So this n and n2 are different. In fact, we might not be able to find any upper bound which might work for all such elements. But if you're working in a Noetherian ring, we can find an upper bound such that if you raise the radical to certain power, it will actually come back in I. For every element it works, but we can have an n which will work for the entire radical for Noetherian rings. So that is our proposition. So in a Noetherian ring, every ideal contains a power of its radical. not true otherwise. And corollary is some power of the nil radical of the ring is 0. Again, because you can just put nil radical here, you raise to some power, then you will just get 0. So this follows from Noetherian properties precisely because there are a finite number of elements which will generate the ideal. So radical of ideal is generated by a finite number of elements a1 to ap, and the radical I, these elements of radical I are of this form c1 a1 all the way to cp ap, where each of these coefficients are taken from the ring A. So for each I, we will have ai to the power of ni lying in the ideal I. That is because of the definition of radical ideal. A to the n lies in I, so here for each of them it lies in I. So now we can consider just this following. You raise it, this entire thing, we copy it down here, and we raise it to some power n1 to the np, and this is the power which works for everything. So expanding it, you use multinomial, this theorem instead of binomial theorem, you use the multinomial theorem to expand it. So multinomial expansion will give you linear terms, but every term will have this factor ai to some ni, and so for every linear term will have such a factor. That would mean that it will lie in the ideal. So thus you raise it to such a power, it will lie in the ideal I. And again, it works precisely because we have finite set of generators, so we can work with the multinomial theorem. And this is the upper bound. So this is the upper bound, and see how this upper bound is critically linked to these ni's, which ai to the ni. It is just sum of these ni's, and these ai's are the generators a1 to ap.